Hi class, welcome to exercise 7i, graphs of circles. And in this lesson, your examples and pre-learning will be example 21, sketching a circle. And your pre-learning for this example will be questions 1 and 2 in the new book and question 4 in the old book. And the other example is example 22, intersecting circles and lines. And your pre-learning for this example is questions 8 in the new book or question 11 in the old book. Unfortunately, today you're not going to be able to avoid circular reasoning. So we best get on with the lesson. We saw on the lesson on functions that circles fail the vertical line test. And this means that they're not functions, i.e. there's no y equals f of x, which was a convenient fact when we're working on polynomials. But I can draw a circle on the Cartesian plane, like this one. So for some point x and y on the circle, do you think that there's a relationship for x and y? i.e. the x and y for each point on the circle. So what do you think? Well, the answer is yes. So throughout this lesson, we need to remember these three facts if we want to describe the circle as a relation between x and y. First, we use our old friend Pythagoras and his rule that states for any right angle triangle with side lengths a, b and c, that the length a squared plus the length b squared will equal the length c squared. Secondly, the definition of the Cartesian plane is that the x and y axes are perpendicular, i.e. right angles. And finally, we define a circle by starting from a point, such as this one, and then measure the distance r, which I'll do officially with this ruler. I think I got one of these lengths wrong here. So I've used 3 centimeters here, but all of these are some magical distance r. And this length here we define as the radius. And of course the radius is measured from that point in the middle. And our circle is every point that, once I adjust this picture, will be that distance from the center. So let me just write that down. A circle is every point that is a distance r from the center. So with these facts about the Pythagoras theorem, the Cartesian plane, and the definition of a circle, let's dive straight into GeoGebra using this applet to give a detailed explanation of the relationship between the x and y values of every point on a circle. So here is a circle, and we can alter the size of the radius by moving r. Now if I drag this point around, it'll let us see how the radius defines what this circle is. Now just let me make this radius 3. So now we could say that the circle is every point that is a distance of 3 from the center of the circle, which is this point 0, 0. And you can see if I drag this point all the way around the circle, the radius remains 3. Now let's just put a triangle in this circle, and you can see that the two lines that are not the radius are perpendicular to each other, precisely because they're running parallel to the axes. So that means that we've got a right angle triangle with the radius as the hypotenuse. And the length of these two other sides relate to the point. The one that's running along the x-axis must have the x value in the point as its length. And the one that's running parallel to the y-axis must have a length that is the y value in this point. Now as you can see written over on the right here, in this case x is 253 and y is 1.6. So that means that x squared plus y squared is 6.42 plus 2.58. And add them together, that's 9, which is the hypotenuse squared, right? In fact, by the Pythagorean laws on right angle triangles, the length of each of these parallel lines squared and added together must equal the length of the hypotenuse squared. So no matter what point we make, despite there being different x and y values, because the hypotenuse is the radius, it's always equal to 3 in this circle. So x squared plus y squared must always equal 3 squared, i.e. 9. Isn't that amazing? If we have another look at the text I've got on the right here, you'll see that I'm not actually using the Pythagorean proof. It's just a direct calculation on the x and y values. But you should be able to use the Pythagorean laws to prove this fact yourself. Now, if I move this point, no matter which point I move to, this is just adding the square of the x and the y values together, which will always be the radius squared. Still 9, see? And it's always going to be 9. Now, in the blue text, you can see that I've written while all circles are x squared plus y squared equals the radius squared. So in that case, it's 9. But you might have noticed that I've kept the point in this quadrant of the plane, where x and y are both positive. Will this be true in other places? Surely, x and y being negative will change things. I'll give you a second to think. Alright, let's move it to C. Well, it does not affect the formula. If you had your thinking cap on, you probably would have realised that if we square a negative number, it's the same as squaring the positive number of the same size. So, for example, minus 1.5 squared is the same as 1.5 squared. So we'd still get the formula x squared plus y squared equals r squared. And it totally fits in with using these triangles too, doesn't it? I mean, even if the x value is minus, the length of this line is actually 2.34 because there's no such thing as a negative length. Now, as we know, circles fail the vertical line function test. So making a table isn't that easy, but we have 4 easy points that we can mark out there. And these are the points on the axis, which are exactly the radius distance away from the middle. So here we've got x equal to 3 and y equal to 3. And of course the x value here is 0 and the y value back there was 0 as well. And while we've got the positive 3, we've also got to have the negative 3x and negative 3y. So they're 4 easy points to know that it's 3 away from the center. Now, despite it not being a function, you could look at a circle as 2 functions being drawn on the same graph. So if we recall, the definition of a function is that I can only have one y value for any particular x value. So I've done a little bit of algebra for you here. So here's the formula, x squared plus y squared equals r squared. And if I put the x squared on the other side, and then take the square root of y squared, we end up with y is equal to plus or minus r squared minus x squared. Okay, and of course there's going to be a positive and a negative version of a square root. So you could think of the semicircle on the top half as the function of this square root with the plus sign in front of it, and the bottom half is the function with a negative sign in front of the square root. So with a circle that has a radius 3, when x is 3 or minus 3, the square root of r squared minus x squared is the square root of 3 squared, which is r, plus or minus 3 squared. So therefore, y is going to be 0. And here you can see when x is minus 3, y is 0. And when x is 3, y is also 0. And you can see these values reflected in the table. Now by extending n here, I can make this table grow with different values of x. Yes, I know I'm a little too proud of my dynamic tables. So in this table, I have the x value with the positive value of y associated with that in the second row, and the negative value of y in the bottom row. Hopefully you can see that the y values are symmetrical around 0. So in other words, when x is minus 2.5, y is 1.66, as you can see with this point here, and looking at the table. And when x is 2.5, y is also 1.6. So you can see we're symmetrical around the y-axis there. But there's also some symmetry with the x-axis. So while x is equal to 2.5, y is around about 1.6, you can see in the table here, y could also be minus 1.66. And let's have a look at that with the point. And of course you'd find the same thing over at minus 2.5 and back again. So hopefully you can take away from this the formula x squared plus y squared equals r squared, but also the pros of using symmetry. And when we go back to OneNote, we'll have a look at some of the cons of the symmetry here. All right, let's go back to OneNote. All right, let's formally state the rules for circles that have a center of 0, 0, such as this one here. and they have a radius of r. Now each point has an x value and a y value, and let me just mark that point. And the x value can be thought of the length of the line here, and the y value could be thought of the length of this line. So looking at those lengths of lines, we have a right angle triangle here. So by Pythagoras, that x squared plus the y squared has to equal r squared. And when we're trying to find the value of a y related to any of the x values, we need to remember that because a circle isn't a function, you must use the algebra and definitions. So therefore, for the circle x squared plus y squared equals r squared, we could rearrange that equation by subtracting x squared from both sides. And then when we take the square root of both sides, we're left with y is equal to plus or minus the square root of r squared minus x squared. So this means that if x was equal to some number a, then two y values relate to this x value, i.e. x is equal to a with y equal to r squared minus a squared, or x is equal to a and y is equal to minus the square root of r squared minus a squared. And obviously both of these are points on the circle, and the top one here is the a for the x and the plus square root, and the one at the bottom is the one with the minus sign in front of the square root. And also let's note that while x squared plus y squared equals r squared is not a function, y equal to the square root of r squared minus x squared is a function, and y is equal to minus the square root of r squared minus x squared is also a function. So that means that both the top and bottom semicircles are functions. It might actually be an interesting exercise for you to try and think about what the domains and ranges are for these functions. And one other thing we want to learn is how to find the intersection between a circle and a line, such as this circle here and this line here, with the equation y equals mx. So to find these intersections here, we're going to use substitution. So in other words, if a circle is described as x squared plus y squared equals r squared, then because that line says y is equal to mx, then I'm going to rewrite that, putting mx in for y. So this means the equation is now x squared plus m squared times x squared is equal to r squared. So we're going to now solve for x. And the best method forward there is to start factoring out x on the right here. And of course, x squared times 1 is the x squared, and x squared times m squared is also m squared times x squared. And now if I divide both sides by the 1 plus m squared, we end up with x squared is equal to r squared divided by 1 plus m squared. And therefore, x is going to equal plus or minus the square root of r squared divided by 1 plus m squared. So therefore, we have two x values or two solutions, as you saw on our graph. But can you think of an easy mistake to make? Well, once you've found the possible x values, you need to get the right y values, right? Because any intersection is a coordinate. So to demonstrate this, let a equal the square root of r squared divided by 1 plus m squared. And let me mark them in on this circle. So we have a positive and negative value there, right? Now, you need to make sure that the y value associated with these points sits on the line. For this a here, we have the two y values, and clearly this is good and this is bad. And similarly for negative a, we've got the two possible y values, with this one being bad and this one being good. So obviously, you need to substitute your x values into the linear equation to get the right y value. Alright, so at this point, you really should pause the video and do the building understanding questions that translates to questions 1, 2, and 3 in the old book, because we are coming up against a new topic here and you should practice the fundamentals before you stretch yourself in the other examples. Alright, I'll see you in that next section. When a circle with a radius r has 0, 0 as its center, then it can be described as a relation x squared plus y squared equals r squared. So therefore any point AB on this circle, and let's not forget our radius here, will have the relationship that a squared plus b squared equals r squared. And we know that by using Pythagoras' theorem, because the point AB relates to the x value A and the y value B, and lines running parallel to these axes form a right angled triangle with the radius. Also, if you're given the relation in the form x squared plus y squared equals A, then that's the same as saying x squared plus y squared equals the square root of a squared. And so that means if we're given x squared plus y squared equals to this number that's not squared, we just end up with a circle that has a radius of its square root. So once we know what the relation is describing our circle, we draw the circle by 1. Marking the center, which in today's class will be 0, 0. Later on in this unit, we'll actually look at circles with different centers. And then 2, we draw a circle that has the radius square root of a. And don't forget to mark in significant points like intercepts. Also, to improve the accuracy of your drawing, you may wish to find a point that matches a particular x or y value. So if we wanted to find y values related to some x, say equal to b, then for our circle, x squared plus y squared equals a becomes b squared plus y squared equal to a when we sub the b in for the x. And from here, you go ahead and solve for y. And no surprises that if you want to find the x values related to a particular y equals, say, c, then x squared plus y squared equals a becomes x squared plus c squared equals a when we sub the c in for the y. And once you got to this stage, you solve for x. Alright, let's have a go at example 21, where we're going to use the equation x squared plus y squared equals 4 to complete the following set of questions. Now in part A, they want us to state the center of this circle. And for all the circles in this lesson, the answer to that is 0, 0. And this isn't a big focus for today's lesson, but we will put a lot more focus on this in another lesson. Alright, in part B, we need to state the radius. Now because our relation here is x squared plus y squared equals 4, well, that's just x squared plus y squared equals 2 squared. So therefore, the radius for this circle will be 2. So far, so good, hey? Alright, part C, the question is, find the value of y when x is equal to 1. Alright, so as I said above, you just need to sub in 1 for x at this stage. So that will make our equation 1 squared plus y squared equals 4. And because 1 squared is 1, subtracting 1 from both sides gives us y squared equals 3. So therefore, y will have to equal plus or minus the square root of 3. So what that means is, of course, is if I was to draw half of that circle, so we've got a radius of 2, so 1's going to be halfway, then these points would have an x value of 1, but the top one has a y value of root 3, and the bottom one has a y value of minus root 3. Alright, let's move on to part D, where we need to find x when y is equal to a half. Alrighty, so subbing in y equals a half, we now can rewrite that equation as x squared plus a half squared equals 4. And I can rewrite that because a half squared is a quarter. And because 4 is 16 quarters, we've got 16 quarters minus 1 quarter when I subtract away the quarter from the left hand side. And that will give us x squared equals 15 on 4. So that means that x has to equal plus and minus the square root of 15 on 4. And as we know from our work with square roots this year, I can take the square root of the top and the bottom. So that's still square root of 15 at the top, but the square root of 4 is 2. So we've got plus and minus root 15 on 2. So we've defined the center and the radius and found a couple of points. But in part E, we're going to actually sketch the graph. and show the intercepts. So throughout this lesson, I've been cutting and pasting a circle because they are so difficult to draw. But seeing this is a demonstration of how to draw it, I won't be doing that on this one. So I first need to draw some axes, and I just want to move this x-axis. Alright, so I'm going to draw the circle first. It's actually not too bad. I'm going to now mark in the intercepts. Now, because we've got a radius of 2, that means that every point on the circle is 2 away from the center 0, 0. So we would have positive 2 in the x direction and negative 2 in the x direction. And the same for y. And the reason why I drew the circle first and then the intercepts is that if your circles are a bit wonky, sometimes it is much better to mark in the intercepts after you've drawn it. And that's because it can be quite difficult to make it stick to your intercepts. So really, we're just going to fake it until we make it. Alright, and I just want to take a note here that it might be fun to mark in the points from part C and D. So for part C, we had that point x is equal to 1, and that's around about halfway there. So then we had the points 1 and the square root of 3, and 1 and minus root 3. And we also had the other one that had a y value of a half, and the x value on the right here was square root of 15 over 2, and on the left we had negative square root of 15 over 2. And even though I thought I drew it well, you can see that it is really flat at the top there and slopes away too hard in the bottom right quadrant. But anyhow, that's the best I could do by hand today. What you might want to use these points for is, like, before you've made the circle, you might sketch out a couple of points like this on graph paper to guide yourself to draw a really good circle. But as I said, if you just draw it the best you can and mark all the points in correctly, then you should be happy with that at this stage. Alright, so that's the end of this section. So pause that video now and do questions 1 and 2 if you have the new book, or question 4 if you got the old book. And then when you come back, I'll see you in the next section. So as we've covered many times in this lesson, a circle has the equation x squared plus y squared equals r squared. And we've covered many times throughout the year that a line has the equation y equals mx. So the way that we're going to find the intersection of a circle and a line is 1, sub mx for y into the circle equation. Then step 2 is to solve for x. And then step 3 is to sub this x value into the linear equation to find the y of the intersection coordinate. And the reason we choose the linear equation is because if you were to use the circle to find the y, you will probably end up with 2 values for each x value. Alright, let's put this into practice with example 22, where we're going to find the coordinates for the points where the circle x squared plus y squared equals 4 intersects with the line y equals 2x. And I've highlighted coordinates because you need to find the x and the y value. So to satisfy this situation, we know that whatever point we find, x squared plus y squared will have to equal 4. And because y equals 2x, then we can write that equation out now as x squared plus 2x squared equals 4, just by using substitution, because y is equal to 2x, right? Alright, so now when I expand that bracket, we'll get our x squared, of course, but we've got 4 times x squared as well. So we've got 1 plus 4, so that's 5x squared equal to 4, which becomes x squared equals 4 on 5, just by dividing both sides by 5. Now we've got a square here, and to get rid of that, I've got to take a square root of both sides. So we're now left with x is equal to plus or minus the square root of 4 on 5. And you might be tempted to stop there, but of course, you know, we can take the square root of either the numerator or the denominator, and the square root of 4 is 2. So we're going to write that out as plus or minus 2 on the square root of 5. And in our third unit, I suppose, we could have rewritten that again by multiplying top and bottom by the square root of 5 to get plus or minus 2 times root 5 on 5. So we've got our x values here, and as y has to be equal to 2 times x, if we want to satisfy the linear part of this simultaneous equation, then when x is equal to minus 2 times root 5 on 5, then y will have to equal minus 4 times root 5 on 5. And obviously when x is equal to positive 2 times root 5 on 5, then y has to equal 4 times root 5 on 5. Alright, let's have a look at that by pasting in a circle. And to make it clear what circle we're looking at, I better mark in the axis intercepts. And because y is equal to 2x, I can find out what angle that is by using inverse tan. And inverse tan of 2 is 63 degrees. So that's going to let me use my ruler to draw y equals 2x perfectly. And then when I mark in the intercepts, I know that the top one has a value of 2 times root 5 on 5 for the x value and 4 times root 5 on 5 for the y value. And the other point has the coordinates that are almost the same except negative. And that probably looks a little bit messy there, written over the top of the circle, but anyhow, that's the best I could do right now. So this may seem a little challenging to some of you, but it really isn't if you use the line to find the y. It's quite an easy substitution. So having said that, you should really pause that video now and do questions 8 if you're working with the new book, or question 11 if you're working with the old book. And the exercise in your textbook has linear equations that are all going through the origin like that. So if this is a little too easy for you, I've also created 2 challenges that you might want to try. And these might require some of your amazing quadratic skills. And challenge 1 is, what are the points of intersection for the circle x squared plus y squared equals 4 and the line y equals x on 2 minus 1. And the second challenge is, find a c so that the circle x squared plus y squared equals 4 and the line y equals 2x plus c has exactly one solution. My hint for you on this one is that sometimes discriminating is good. Alright, I'll see you in the summary. The rule for a circle can seem mysterious at first, but once we've used the Pythagoras theorem, it should seem pretty clear. And this concept of applying Pythagoras to a circle will help us take trigonometry to a new level. But more about that later on in the year. And later on in this unit though, we're going to learn rules for circles that have a center that is not in the origin, i.e. 0, 0. So it's really important that you get the skills of these circles as we introduce them with the origin as the center. Alrighty, so in this lesson, a successful student will know the form of the Cartesian equation of a circle centered at the origin with a radius r. Be able to sketch a graph of a circle centered at the origin using the radius to label the intercepts. And finally, know how to find the points of intersection of a line and a circle. So I hope you've enjoyed our start to our new block. Keep working hard. As you can see from my warning earlier in this summary, this will be extended later on in this block. So we'll see you in the classroom or the next video. Bye.